Inside this glass block, a ray at 30 degrees escapes into the air. But increase the angle to 41.8 degrees and the emerging ray runs alongside the surface. Increase it again to 50 degrees and the ray no longer leaves, it reflects back into the glass. Refraction is a change in direction when a wave changes speed at a boundary. At normal incidence, speed and wavelength change, but the ray does not bend. At oblique incidence, it usually changes direction as well. Refractive index, n, compares the speed of light in a vacuum with its speed in a material. n equals c0 divided by v. For this glass, n is 1.50, so the speed is about 3.00 times 10 to the 8 divided by 1.50. 2.00 times 10 to the 8 meters per second. The source fixes the frequency, so frequency does not change when the light crosses a stationary boundary. From v equals f lambda, a lower speed means a shorter wavelength. The speed and wavelength in the glass are both 2/3 of their values in air. Now, send the ray from the air into a flat face at 48 degrees. Every angle is measured between the ray and the normal, never between the ray and the surface. Glass has the higher index and lower speed, so predict that ray bends towards the normal. Snell's law is n1 sine theta 1 equals n2 sine theta 2. Substitution gives 1.00 sine 48 equals 1.50 sine r. Therefore, r is 29.7 degrees. That is smaller than 48 degrees as predicted. Reverse the arrowheads and the light follows the same path back. Refraction is reversible. Follow that reverse path. The ray enters the curved face along a radius, so it meets that surface normally and does not bend there. When it crosses the flat face into air, it speeds up and bends away from the normal. If we increase the internal angle of incidence, the refracted angle also increases until the transmitted ray travels along the boundary. Its refraction angle is now 90 degrees. The corresponding internal incidence angle is the critical angle, theta c. For this glass-to-air boundary, Snell's law gives 1.50 sine theta c equals 1.00 sine 90. Therefore, sine theta c is 1 divided by 1.50, giving 41.8 degrees. In general, sine theta c equals the lower refractive index divided by the higher one. There are 3 distinct cases. Below the critical angle, a transmitted ray exists with a reflected component as well. At the critical angle, the transmitted ray runs along the boundary. This is not yet total internal reflection. Above it, no propagating transmitted ray remains. The light reflects entirely back inside. Total internal reflection needs 2 conditions: travel from a higher refractive index to a lower one, and an incidence angle greater than the critical angle. Light incident from air onto glass cannot undergo total internal reflection at that boundary. The law of refraction still applies, so the reflected angle equals the incident angle. For a ray box investigation, draw around a rectangular block, mark the incident and emerging rays, and then remove it. Then reconstruct the internal path. With a semicircular block, direct the ray through the curved face along a radius, and then measure I in the glass and R in the air for several angles. Plot sine R on the vertical axis against sine I on the horizontal axis. Snell's law predicts a straight line whose gradient is the refractive index of glass divided by that of air, which is about 1.50. Use a line of best fit. Estimate the critical angle by bracketing it between the largest angle with an emerging ray and the smallest angle showing total internal reflection. Ray width and the center alignment limit the precision. For AQA, a step index optical fibre applies the same rule at the core cladding boundary. The core has a uniform refractive index and the cladding has a slightly lower one, with an abrupt step between them. Light meeting that boundary above the critical angle is guided by repeated total internal reflection. Cladding is not a mirror coating. Its lower refractive index provides the lower index boundary required for TIR, which protects the core boundary and helps stop light crossing between neighbouring fibres and mixing their signals. Information is sent as pulses, which must remain separate and detectable. Modal dispersion broadens a pulse because different modes follow different path lengths. A near-axial route is shorter than one involving many reflections, so the components arrive at different times. A single-mode core largely removes this effect. Material dispersion has a different cause. Refractive index depends on wavelength, so the spectral components of one pulse have different propagation times and arrive at slightly different times. A narrow spectrum source reduces this broadening. Absorption is signal loss rather than pulse spreading. Some optical energy is transferred to the fibre, so the pulse weakens with distance. High purity fibre and low absorption wavelength reduce the attenuation. Broadening can make neighbouring pulses overlap, absorption can make them too weak to detect. The same checks apply at every boundary. Measure every angle from the normal. A higher index means a lower speed. Use Snell's law. For TIR, check both that light travels towards a lower index and that its incidence angle exceeds the critical angle. In the next lesson, we will examine diffraction and the single slit.